Okay, AP Chemistry students, welcome back to Unit 7, Dynamic Equilibrium. Okay, equilibrium is a process in which we start dealing with the reversible reactions, and we started talking about this a little bit earlier last week, and now we're going to go into a couple of things that we didn't exactly go over during class, including how the size of the arrows can affect the graphs of the reactions. Okay. But the first thing to remember is that a reaction can go both ways. It can go in the forward direction, in which the reactants are converted into products. It can also go the reverse direction, in which the products are converted back into reactants. Okay? Equilibrium is reached when the speed or the rate of the forward reaction is equal to the speed or the rate of the reverse reaction. That is equilibrium. Okay? Equilibrium is not equal concentrations of product and reactant on both sides. Equilibrium is when the speed of the forward reaction matches the speed or the rate of the reverse reaction. Okay? And we indicate reversible reactions with a double-headed arrow looking like this right here, to show that there is a forward and reverse reaction. Okay. And again, please be careful. Equilibrium does not mean that you have the same amount of product and reactant on both sides. Okay. Equilibrium is only reached in a case where the speed of the forward reaction is equal and opposite to the speed or the rate of the reverse reaction. There are situations in which these double-headed arrows aren't necessarily equal, and the products could be favored or the reactions could be favored. Nevertheless, the rate of the forward reaction is still equal and opposite to the rate of the reverse reaction when equilibrium is reached. Okay, there are three different types of differently sized arrows we can look at, and the first I have, excuse me, the first I have circled there or squiggly there with a yellow sign or yellow color, and that is when both arrows are equally sized, and that could indicate that the forward and reverse reaction are both equally favored. However, this equal-sized arrow is also just a general symbol for when a reaction is at equilibrium, okay? In fact, you will most often see on the AP exam that the arrows are equally sized, even though the reactants could be favored or the products could be favored. So just keep in mind that you will most often see an equally sized arrow, and you cannot just make the assumption right off the bat that the reaction is equally favored on both sides. They will have to tell you whether or not the reaction is favored one way or the other, or give you enough information that you could solve for it, and we'll talk about that in a later lesson. The second type of error that you could see is in the case in which the forward reaction is favored. So you'll see a longer forward arrow and a shorter reverse arrow. This indicates that the products are favored. The rate of the forward reaction is still opposite or still equal to the rate of the reverse reaction. You will just end up with more product than you will reactant. And then the reverse case of that is in which the reverse reaction is favored, so the backwards arrow is longer than the forward arrow to indicate that the reactants are favored. Okay? The rate of the forward reaction is still equal to the rate of the reverse reaction. You will just end up with more reactant in this situation right here than you will product. Okay? Always remember, equilibrium is established when the speed or the rate of the reverse reaction is equal to the speed or the rate of the forward reaction. I forgot how I just said that, but the speed of and the rate of the forward reaction is equal and opposite to the speed or the rate of the reverse reaction. Okay. These different situations in which case the products are either equally favored or one side is favored over the other can be illustrated graphically. Okay, and we're going to go over those three situations. Right here I have a graph of concentration versus time, because when we're looking at the rates of reactions, we measure that in the change in concentration per time, just like how you would measure the speed of the car in miles per hour, a distance traveled per time. When we monitor the speed of reactions, we monitor the change in the concentration as a unit of time. And I have put arbitrary units of concentration here Those could be any number, but they are in the unit of molarity. And the time over here we're going to have in seconds. Okay? At the start of the reaction, you are always going to have a certain amount of reactant, okay? So before the reaction begins, you will always have a certain amount of reactant. Before the reaction begins, you'll never have any product because the reaction hasn't actually started yet. But in a situation in which both the reactant and product are equally favored, you will start to see when the reaction starts, the reactant will start disappearing as it's converted to product, and it will eventually flatline or become constant. Simultaneously, the product will start to form and again will level out and remain constant throughout the rest of the reaction. There is a way to tell when equilibrium is reached with this type of graph, and it occurs as soon as the slopes of the line stop changing. So when both of those slopes stop changing, and we'll make an arbitrary guess, they stop changing as soon as they begin flattening out. And I think we could safely say they start beginning to flatten out about right there. So I will illustrate that on this graph, and you should illustrate this on your sheet of paper. This is the point in which equilibrium is reached, because the rate of the forward reaction is equal and opposite to the rate of the reverse reaction. And we say that both the product and reactant are equally favored because when they start flattening out, when they reach equilibrium, they're both at roughly the same concentration. And that's what causes this same sized reverse and forward arrow. So we say equilibrium is reached, so the products and reactants are equally favored. Let's look at one of the other scenarios. In this case, the reverse reaction is favored, and the reverse reaction is favored, and the forward reaction is not favored. Okay, so we are going to have a lot more reactant this time than product. So in this situation right here, we will still have, at the very beginning of the reaction, no product forming, and then at the very beginning of the reaction, we will have a lot of reactant. Okay? But as the reaction progresses, we will still see that some of the reactant starts disappearing. However, it's going to level off a lot quicker. Or in other words, not much of it is going to be used. Similarly, with the formation of the product, because the reverse reaction is favored, we are not going to form that much product at all. Okay? We are not going to form that much product at all. So at the end of the reaction, we have a ton of product up here still because it didn't reduce down as much. And at the end, we did not form that much product here. Okay? So we could say this is probably like 0.7 molar, and this is probably 0.1 molar. Again, arbitrary values. They could be any number if that was 1.0. Equilibrium is still established when the slopes of the line stop changing. So the rate of change is equal and opposite in both directions, and that's going to be about right there. So this is equilibrium. Because remember, at the end of the day, equilibrium is reached when the rate of the forward reaction is equal and opposite to the rate of the reverse reaction. It's just in this case, we will end up with more reactant than product, since the reverse reaction is favored. Let's look at the final scenario in which the forward reaction is favored. We have 1.0 molar here, about right here, 0.5, and then 0.0 molar down there. This is the concentration of our reactant, and down here is the concentration of our product. In this scenario, when the forward reaction is favored, we are going to form a lot of product. Okay? We're going to form a lot of product. So pretty much all of the reactant is going to get used up. And then barely any of it is going to be present or left over at the end of the reaction. Conversely, because we're forming a lot of product, we're going to see a huge spike in the amount of product being formed. And again, they always level out because that's when equilibrium is reached. And at the point where the lines stop changing or the slopes stop changing is equilibrium. And at the end of a reaction in which the forward reaction is more favored, you will end up with a lot more product than you will reactant, because everything is shifting over to the right-hand side, though the rate of change are still equal here. But nonetheless, the products are more favored than the reactants. Now you should be able to identify and determine how the equilibrium is favored by looking at such graphs. Okay? With a reaction that's more favored in the forward direction, you're going to end up with a lot of product at the end of the day. With a reaction that is favored more towards the reactants, you're going to have a higher concentration of reactants and a lower concentration of product. For a reaction that's equally favored, in this, there's not really a whole lot of situations where I can think of that they're both equally favored, but the concentrations of both will be equal when equilibrium is reached. So go ahead and rewind this video if you need a reminder on any of the parts, and give the following questions a try on Nearpod. We'll see you for the next video.